In order to tell if a number is divisible by 2, 3, 4, 5, 6, 9, or 10, you have to be very familiar with the divisibility chart on page 152. If you rely on that chart for a problem like number 1, the rule says that for a number to be divisible by 2, the last digit has to be an even number. Since 8 is an even number, 508 is divisible by 2. For a number to be divisible by 3, the sum of the digits has to be divisible by 3. That means if you add the digits 5 plus 0 plus 8, which is 13, the sum 13 has to be divisible by 3 in order for 508 to be divisible by 3. Since 13 is not divisible by 3, neither is 508. For a number to be divisible by 4, the last two digits have to form a number divisible by 4. The last two digits of this number are 0, 8, which is the number 8. Since 8 is divisible by 4, 508 is divisible by 4. For a number to be divisible by 5, the last digit has to end in a 0 or a 5. This number does not end in a 0 or 5, so it's not divisible by 5. For a number to be divisible by 6, it has to be divisible by both 2 and 3. 508 is divisible by 2 but not 3, so it's not divisible by 6. For a number to be divisible by 9, the sum of the digits, which is 13, has to be divisible by 9. Since 13 is not divisible by 9, neither is 508. For a number to be divisible by 10, it has to end in a 0. Since 508 does not end in a 0, it is not divisible by 10. So your answer for number 1 would just be 2 and 4. For number 2, if we look at the last digit, it's even, so that makes it divisible by 2. We have to get the sum of the digits to see if it's divisible by 3. 4 plus 3 plus 2 is 9. Since 9 is divisible by 3, so is 432. For 4, we have to look at the last two digits. They form the number 32. 32 is divisible by 4, so is 432. For 5, we have to look at the last digit, but it's a 2, not a 0 or a 5, as it must be to be divisible by 5. For 6, we have to see if it's divisible by both 2 and 3, which 432 is, so that makes it also divisible by 6. For 9, we have to look at the sum of the digits, which is 9. Since 9 is divisible by 9, so is 432. 432 does not end in a 0, so it's not divisible by 10. To tell if a number is prime or composite, you have to know the definitions of prime and composite numbers. A prime number is a number greater than 1 that has only two factors, 1 in itself. Another way to think of that is the only numbers that can go into a prime number are 1 and the number itself. None of the divisibility rules would work with it, and there are no other numbers that the number is divisible by. A composite number then is a number that has more than two factors. Once you see that a number has more than two factors, then you know it's composite. If we take number 17, we have the number 34. 34 is an even number, so besides 1 and 34, you also know that it is divisible by 2, which makes it composite. You don't have to list all of the factors of 34 to see if it's composite. As soon as you find more than two factors, you know it's composite. For number 18, we have the number 29. 29 is not an answer to any of our basic facts, but if we try some of our divisibility rules, especially the ones for 3, 5, and also seeing if it's divisible by 7, even though we don't have a divisibility rule, is necessary. We know 29 is not divisible by 3, it's not divisible by 5, it's also not divisible by 7, so that makes it prime. And now, since 29 has only two factors, 1 in itself, 29, that makes it prime. For number 21, the number is 51. It is not an answer to one of our basic facts, and it's also not even, so it's not obviously composite until we try our divisibility rules. We try our divisibility rule for 3, 5 plus 1 equals 6. Since 6 is divisible by 3, so is 51, so that makes it composite. Your divisibility rules come in handy when it's a number that's not an answer to one of your basic facts, and it's not easily recognizable to be composite. So use your divisibility rules whenever possible here. For prime factorization, we have to break a number down into a product of its prime factors. What that means is our final answer is going to use only prime numbers that can be multiplied together to get our original number, like in number 5, 48. So we have to think to ourselves, what numbers can we multiply to get 48? There are different sets of factors that you could choose. It doesn't matter which set of factors you start with, you'll end up with the same final answer. For 48, I'm going to try 6 times 8. Since neither 6 nor 8 are prime, or actually 6 nor 8 is prime, we have to break both of those numbers down into their factors. To get 6, I could multiply 3 times 2. Since 3 and 2 are both prime, I'll circle them, and that part of the factor tree is complete. For 8, I know 2 times 4 gives me 8. 2 is prime, so I'll circle that, but 4 is not, so I have to continue to break that down. 2 times 2 gives me 4. 2 is prime. Now that I have prime numbers circled at the end of all of the branches of the factor tree is done, but that's only your work. In order to give your final answer, you have to start with the smallest factor, smallest prime factor. In this case, it's 2. There are 1, 2, 3, 4 2's. So we're going to write 2 to the power of 4. We're going to use exponents whenever possible. And then we'll put times 3. Again, this final answer has to be put in numerical order. There are 1, 2, 3, 4 2's times 3. This is the part that has to be the same. Your factor tree may look different if you choose to use other factors, but your final answer will come out to be the same. For number 21, we have 81. To get 81, multiply 9 times 9. Since 9 is not prime, we have to continue to break down both 9's. 3 times 3 is 9. 3 is prime. And here 3 times 3 is 9, and the 3's here are prime. So our final answer will only include 3 to the power of 4, since there are 4 3's. Sometimes there's only one prime factor to be included. Sometimes there are even more than 2. It depends on each number. The key is you have to get down to all prime numbers at the ends of the branches, and you need to list your final answer in order from lowest prime factor to highest prime factor, using exponents when necessary.